From Chicago, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
There are companies in the world that build electrochemical machining machines, equipment. They're all
very cheap,
in Europe.
Right?
Yeah. Cheapest one was at the time $500,000, $600,000, something like that, and they just went up from there. And so I really, just because I didn't have the money, built our own machine from scratch.
That was Daniel Harrington. Daniel is the founder and CEO of Voxel Innovations, a manufacturing company based out of Raleigh, North Carolina. Voxel is a pioneer in pulsed electrochemical machining, an efficient, accurate, and specialized approach to machining high-quality metal components for medical, aerospace, energy, and other industries. Before starting his own company, Daniel worked as a professional race car driver in both the Indy Pro and Grand Am series. He spent several years with the Advanced Research Project Agency for Energy, ARPA, in Washington, D.C., and worked as an independent advanced manufacturing consultant. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast. Remember, you can listen to the show anywhere you download your podcasts, including Spotify, Apple, Amazon, or Stitcher. Daniel, welcome to the show today. Excited for the conversation. We're going to be talking in gory detail about post-processing for 3D printing. So why don't we get started? Why don't you kind of share a little bit about your beginnings, where you're from, kind of what's kind of the origin story for kind of where you ended up today?
Sure. Yeah. So I went to NC State for undergrad in mechanical engineering. And actually at the time I was racing cars full time. So while I was in school. And so I sort of had this early career as a race car driver.
How'd you get into that?
Yeah, I started with a driving school with my dad back when I was 16, convinced him to take me to driving school with him for his birthday. And then became sort of a hobby on the weekend with him. And then I won enough races. People thought I should sort of think about it more seriously, and was able to climb the ranks, mostly focused on open wheel cars like Indy cars. Didn't quite make it to IndyCar proper, like Indy 500, but we raced in a series called Indy Lights, which raced at all their tracks right before their races. It was a feeder series to the IndyCar series. So I did that and sports car racing, but basically I drive anything people would let me. If I got the chance, I'd jump in a car and drive. So I was doing that in undergraduate, and then after undergraduate degree, I was more or less doing that full time until the recession hit, and raising money to go car racing was more difficult, let's say, then. So I knew I had this passion for manufacturing and energy and seeing something physical be made. I didn't really know how to direct that interest. And so I went to graduate school at Duke, got a degree in engineering management, which is kind of like an MBA for engineers, shorter, compressed, less heavy on the finance, more heavy on the sort of innovation management or what have you. And from there, I went to work at the Department of Energy in a group called ARPA-E, which is kind of like DARPA for energy projects. So they funded advanced research projects all over the map, new natural gas powered vehicles, turbine cycles, new ways to manufacture magnets. And that was an eye-opening experience for me. I think I was immediately the dumbest person in the room there.
Were you evaluating like proposals or like project managing?
So they've got a group there, they call it tech to market, but it's really just making sure that the projects they fund have a pathway and an eye towards commercialization. Okay. They don't just die as a research project and go nowhere. And so, it's a small piece of the overall project budget, but really critical to make sure that those projects succeed. And so I was often helping them think through their plans for how they might commercialize technology, but as important with that, trying to make connections to other people in industry that could help them succeed once they got through the ARPA-E funding phase. But through that process, I had to and enjoyed reading all the technical proposals and sort of diving into the technology piece of it, and was really enamored by how many great ideas there were out there for energy innovations. But after doing that for a year and a half or so, I sort of wanted to be doing it myself. But the other thing I realized is that manufacturing can play a really critical role there. It's kind of an overlooked element of these innovations. Often manufacturing or new capability will enable some new innovation that people couldn't have done 10 or 20 years ago. And more than that, once you get, so since I was focused on the commercialization side, you can have a great idea all day long, but if it costs too much money, it's never going to fly. And so manufacturing can be a really critical piece of that, or designed for manufacturability to making those cool ideas turn into reality. And so I left ARPA-E to essentially do something on my own. I wasn't sure what it was going to be. I didn't even intend to start a business. I just wanted to be out in industry trying to help make something innovative in the manufacturing, energy, whatever nexus. It was unclear at the time.
So you just quit and did something else?
Yeah. I had a sort of friend of a friend who had a business in New Jersey called Medem, and they are now part of GE Power, and they drill cooling holes in gas turbine blades. And I started doing some work for them, actually trying to understand how additive manufacturing might impact their business. And so that was really my first, I learned more about it while I was at ARPA-E, but really got invested in it, doing this consulting work for this company and trying to think about what its implications might be in gas turbine engines, which turned out there are a lot of them, maybe not affecting them directly, but it was a very educational opportunity for me. And then was also introduced to the technology, or the sort of general technology that they worked with, which is electrochemical machining. So that's dissolving metal with electricity and chemistry instead of printing it together, building up additively. And that really, additive is really cool. I was quite enamored with that technology, but by the time I started getting excited about it, in many ways, the horse had left the stable. There were lots of companies working pretty feverishly on technology there, making additive printers, applying it in really unique ways. It would have been fun to jump in there too, but I saw this electrochemical machining process as a technology that was really underutilized given the benefits it had. And part of that was because the technology is very hard. There's sort of this interplay with chemistry and electricity and material science that is not that common in manufacturing. People are usually used to melting things or cutting things, not necessarily dissolving them. And so that sort of appealed to me as what seemed like a niche process right now might have some room to grow to be something not so niche and could supplant other processes or aid others, particularly additive. Since I looked into it early on, one of the refrains I kept hearing was surface finish is a challenge for fatigue life and all these other issues. So the common comment was, I'm not sure what this electrochemical machining is you're doing, but can you fix my surface finish problems? And so I thought, well, maybe there's something here. So the sort of short version of that is, after being exposed to additive and electrochemical machining, I thought there was an opportunity to build a business around really just electrochemical machining, with additive being a potential outlet or industry for us. Originally, I was supposed to be with a couple other partners, and life things happened with those partners, and end up with me just starting the business on my own. I really just fell into it. Like I said, I did not set out to start a business. I just got excited about the technology and the potential here, and felt like it'd be wrong to not start a business after all the time and effort I went into thinking about it.
So what does it mean to just, I mean, I started, so I've been in your shoes. I started a business by kind of myself. So what did that look like? Did you have like were you doing this, like getting parts from people and doing it yourself in a lab somewhere? Were you kind of contracting out? How did that look? Did you raise money? What was the path?
Yeah. It's, so there are companies in the world that build electrochemical machining machines, equipment. They're all
very cheap, right?
Yeah. Cheapest one was at the time $500,000, $600,000, something like that, and they just went up from there. And so I really, just because I didn't have that money, built our own machine from scratch, and it was very crude and basic and didn't have much functionality, but you had to learn every single aspect about how the process works and what details matter, which ones don't. And so I sort of spent money that I had in savings and got some money from friends and family, basically raised an initial round of convertible debt from friends and family to try and help me build the equipment. And for 6 or 12 months, it was just me and a 800 square foot sort of rented flex warehouse space, and sit there, design the machine. And we started using Onshape very early on, and design the machine. When I build it, I figured I taught myself how to welded the frame to it, bought some big granite slabs to turn into components of it, found linear motors and axes and other things, found custom power supplies, really cobbled this thing together, found friends that knew about industrial wastewater treatment and could help. They had just finished a PhD or postdoc and knew enough to be dangerous to help me cobble my way through that. And we're also starving, so they were cheap. So, basically pinch my pennies through building a piece of equipment that could do some sort of electrochemical machining. And at the time, I had some ideas on customers, but the thing that I've learned and continue to learn is, as a small company with 1 or 2 people, it's pretty hard to get the attention of a GE or Rolls-Royce or Pratt & Whitney. They think of you as researchers, not as manufacturers, contract manufacturers. And that was our vision all along, is that we wanted to build a contract manufacturing operation, that we don't just do research and turn over what we learn about the process to someone else. We want to actually make parts in volume for these companies in medical and aerospace. So we had some early customers that sort of were interested to learn more about how the process worked and see how it behave on their material system or whatever. And so we did some of those jobs, didn't necessarily go anywhere, but gave us an opportunity to get a little bit of money coming in the door, but mostly a chance to learn, figure out how to interact with them. And then over time, I hired a great first employee who helped me finish out building the machine and take on some new projects. And then we started we had our first electrochemist, sort of fresh out of school, who turned out to be really sharp and helped us develop more technology and how we're heading with our business. We also we realized that getting into contract manufacturing as a couple-person company was going to be pretty difficult, especially given that our technology has a lot of value in these high-value applications, or applications where someone might die if your part fails. So we sort of realized that the time scale for us to get involved in contract manufacturing for a part of a jet engine or an implantable medical device was going to be pretty long. So we kept those relationships going, but then started doing more work through SBIR funding or government-funded research. And if those of you that are unaware, it's non-dilutive funding that allows you to develop your technology, build a sort of an IP base that you can then protect if you got some money to go file patents, or build know-how, but also sort of keep an application in mind. Often they're targeted towards some need out in industry. So those have been very valuable to us to grow our business, grow the technology, but also, the point of those is to solve a problem out in the world, not just sort of do research for research's sake. And that's sort of manufacturing in general is often that way. It's very application focused. And so that helped keep us grounded, that we were always sort of thinking, we're responding to these solicitations with an idea about how we can solve some broader problem out in industry. Maybe it's part of a jet engine or a rocket engine, for NASA, or some new space flight thing for the Air Force, detector for the Navy. They're often, and actually additive finishing, it became a topic and is still a topic for lots of these agencies. So those early years kind of consisted of a smattering of early commercial opportunities and government funded SBIR research.
So what years were these?
That would have been, I think we won our first contract in 2017. So I formally started the business 2015, but all that means is I found a website and a name. I think I hired my first employee mid 2016, and maybe in 2017 or so, we won our first SBIR. Might have been even beginning of 2018. Now I think about it, we had some failed attempts early on, which were educational. But so a couple of years down the road, and really we were just surviving off the sort of convertible debt that we had raised and a little bit of customer money that we get in the door here and there.
For those who haven't gotten down the startup path, so what's convertible debt? What does that mean? Yeah,
so convertible debt is basically it is debt. It's a form of debt. So in theory, you could repay the debt to the lender before the end of the term, but more commonly, it's used as just a intermediary step between no money in the door to raising some sort of round through a formal series of investors or venture capital or whatever it is. And the basic idea is that these people are giving you money, but when you go and raise a round, that money they've given you as debt will get converted into equity at a preferred rate. So it helps offset the risk that they put in their money at a very early stage to you.
Sure. Awesome. And so kind of what does the machine look like? What did the first iteration or even today is like for, I'm guessing most people who listen to this show might be their first time hearing about this process. So can you kind of paint a visual picture of what this looks like?
Sure. So there are three major components to the machine. The one that'll be easiest to relate to is the machining cell, the envelope. And that kind of looks like a sinker EDM machine or a CNC machine or even a 3D printer for that matter. It's just an area with a bed and some axis above it or next to it. And all it's doing is moving your electrode close to your workpiece. So you load a part in, load a tool in, and move it towards each other while you're spraying electrolyte in between the two. So that's sort of the simplest thing to envision, and it can take lots of different forms. Some of these are designed to make really big parts. Some are making really small parts. The other two pieces of major equipment for this is a big power supply. So our process is a low voltage, high amperage application. And so we are often running 5 to 50 volts of potential, but thousands of amps of current. And so these are not common power supplies. And we're also, in our case, we're using pulsed power. So we might run square wave voltage pulses that could be milliseconds to microseconds in width. And so these power supplies are pretty specialized. There really aren't that many people in the world that make them. And then there's a wastewater treatment system effectively. So our process uses a saltwater solution as its working fluid. So EDM uses dielectric. You can use water or kerosene. I should say EDM is electrical discharge machining for those of you that don't know. And we do electrochemical machining, ECM. Often confused, but they are different. And so in our process, our working fluid is usually a saltwater solution. And it can literally be water and table salt, sodium chloride, or sodium nitrate, or something else. And so that is kind of just like a small municipal industrial wastewater treatment system where we supply clean electrolyte to our cell, and pull away dirty electrolyte that has dissolved metal, dissolved iron oxides or nickel oxides and hydroxides, whatever the metal is we're cutting. And then we filter the waste out, do some chemical balancing, chemical additions, change pH and conductivity and some of those variables. And it's a closed loop system. And that there is an outlet where we can pull off the concentrated metal sludge that comes off the machine. So basically the waste. So instead of chips that might come off a CNC machine, we create a brown goo that we get to pull away and send off to get recycled. So those are the three main components of the system.
And so what materials can this work on? I mean, you've mentioned metals and some of the oxides that come off, but like what go through the process of like, what would be a good candidate part or material, or what would the process do?
Sure. So from a material standpoint, it has to be conductive. Basically, that means a metal. If it is metal and it's conductive, we've got a good shot at it. Things that become borderline are something like a semiconductor, which is conductive, but either is very not very conductive. So you might need a ton of voltage to pass current through that. So and that's the most common case is in the semiconductors, that we need really highly doped semiconductors, and we can machine those, but it's kind of rare. So mostly metals is what we deal with. And within metals, generally ECM can machine lots of materials. The ones that have historically been more challenging are refractory metals or valve metals. So think of titanium, tungsten, niobium, molybdenum, rhenium, those sorts of things. We actually are doing some more research now on machining those materials with a different sort of set of parameters we use in our process, and that's proving to be successful. And so really it's a combination of the material and the electrolyte and the type of power you're applying that determines success in a material system. There are obviously some more complex materials too that are sort of interesting for us. So things like metal matrix composites or something that's non-homogeneous. A good example of that that's been around for a long time is aluminum silicon carbide mixtures, AL-SiC. They use them in heat sinks and other things. Those can have large silicon carbide particles in the matrix, and that silicon carbide is inert to our process, so we don't dissolve it. But we will happily dissolve the aluminum that's around it. And so we can sort of free the silicon carbide particles. If those particles are really big, it could be problematic for us. If they're small, it kind of doesn't matter. It doesn't affect us. We actually machine faster because now we're not having to dissolve the silicon carbide. It's just being liberated. So this is a long way of saying is that when you have non-homogeneous materials or materials with a large volume fraction of something that's non-conductive, you need to pay a little bit more attention with our process. Something that's got strands of carbon fiber woven through it would be a real challenge for us. We just hit those strands and not break them down. So homogeneous metals are the best thing for us. And when they do have other elements in them, if they're small, sort of micrometer scale or less, that's best.
And so when you look, kind of keep it in the context of additive, when do you work on the part? Like, so if all metals, like metal parts are they're always welded to a build plate. Like, are they freed when you work on them, or are they on the build plate?
They could be both. Generally, though, they're off the build plate. We find that most people build, everyone has their own build strategies, but a lot of them build them on support structures up off the build plate and then break them off the support structures or wire the EDM them off the build plate. It's just a little bit of a cleaner process. Particularly if they're going to reuse that build plate, there's someone that's doing a lot of additive work. They don't really want to ship you a build plate necessarily. So we're taking it after that, after they've gone through their heat treatment steps. They can make it as hard as they want. It doesn't really matter for us. So we're kind of the end of the line. We've been working on additive applications, and the area that we fit most cleanly in additive thus far has been one or two areas. One, there are surface finish problems in additive. Sometimes it's just for appearance sake. Sometimes it's for fatigue life issues. Sometimes it's the roughness is so bad that you can't actually inspect it doing dye penetrant inspection. You can't see if there's cracks in the material. From what I've seen, the biggest cause of these is downskin surfaces or surfaces that are supported by support structures. So they might not break off cleanly at the surface. They leave sort of what I call macro scale features on the additive print. And that's where our process is the most effective, is taking those sort of extra rough features and machining them down pretty aggressively, but without having to apply force to the process. So this electrochemical machine process is completely non-contact and non-thermal. So we don't have to touch the surface with the cutting tool. That means if you've got a delicate 3D print with a bunch of thin-walled features, we can clean up those surfaces without distorting that geometry. And there are some printing processes, whether it's electron beam melting or maybe some of the free-form powder deposition processes that print with thicker layer lines, with more rougher surfaces, and those really, they just need post-processing just for them to be functional in many cases. And so we find value in working on those applications where they've got really bad support structure remnants, really bad surface roughness. If you're just going to sort of make the surface glossier for appearance sake, there are lots of vibratory finishing, electropolishing methods that are cheaper than our process would be. But if you really care about the precision geometry or sort of maybe targeting a particular surface, that's where our process could be valuable. It's got plenty of limitations, but when you think about this in the context of volume production, where you're not just making 1 or 5 printed parts, but you're making 1,000 of them or 10,000 of them a year, like people are doing in aviation or medical, our process starts to make more sense because you can think about designing tooling for it and really getting through these parts much more quickly with our process.
And has the business still kind of remained the same idea where you want to be kind of that contract manufacturer to do this, or do you want to make machines as well?
We would like to have more of a focus beyond contract manufacturing, but we do have more and more people asking us about building machines. And that's interesting in many cases and could be a good way to grow the business, but it also presents some challenges. Namely, when you develop a process that's complicated like ours, there's a lot of know-how that you can't or don't want to write down, I should say. And if you sell a machine to someone that's going to do anything other than push a button and make a part, you would end up selling some of your IP and know-how to them and essentially making a competitor at the same time. And so we're happy to and have been talking with a number of people about building sort of turnkey systems for them. But that's really, they see our process as a way to make a part that's better, faster, cheaper. They don't really care how it's made, or they just want it sort of in their supply chain or on their production floor. So they really just need a way to push a button, and they could sort of care less about how it works as long as it does work. So those applications are more interesting to us in terms of the machine sales. But I think the contract manufacturing piece still makes a lot of sense because we're continuing to develop new innovations with technology. And if we can still be in that loop of making parts for those customers, that allows us to apply new innovations and efficiencies and improvements to make their part better, cheaper, faster over time, rather than sort of turning that entirely over to them. So it's kind of like additive machines. Many people are leasing these now, or you can lease equipment for some amount of time, or they've got routine software updates or some sort of recurring plan along those lines. When the technology is changing rapidly, you don't necessarily want to be stuck with the same piece of equipment and same limited processes. I don't know that our process is changing quite as fast as additive, but we personally, here at Voxel are making a number of strides, and it'd sort of be a shame for a customer to lose out on that efficiency that we've figured out here. And plus, many customers don't actually want to deal with the waste treatment side of things. right? So we take care of all that stuff. We get rid of the waste for them, manage all the regulatory pieces around that. And so it can be just an easier solution to send it to us.
So how do customers find you? Like, can you just tell kind of like what's a typical customer story, or go into any detail that you can that's not IP sensitive?
I mean,
just maybe generically.
I think our first customer, it took me 2 years to get to the right person to agree to a quote. It hasn't gotten, it's not that bad anymore. But when you deal with big companies, and often our process, like I said, we focus on what you call parts with high engineering content, or they've got a trade-off between performance and cost. So I like to think of these parts as, if you could make it more efficient or better, they'd pay you more for that. That's not the case necessarily for a cell phone case. If you can, they mostly just care about making it cheaper. And we do have some customers like that, but largely, in many cases, they want to make this part better in some way. And that's kind of how we enter the conversation. So those often are larger businesses too. They're in aviation or medical or some energy application. And so it can take a long time to go find the right people in those things, in the right silos. And so that for me, has meant networking through trade shows and conferences, really just walking up to people that are speaking at these technical events and slightly pestering them, but mostly trying to learn about what their problems are in manufacturing. I do a lot of work just on my own, trying to understand how other components are made and what their challenges are. Sort of this cycle of research through online sources, Google, academic journal articles, whatever, and then go call people, literally cold call people that might be, the easiest to talk to are those in academia that maybe have worked with industry before. They might have some insight, can point you in the right direction a little bit more, and then go try and find the technical experts at the companies and understand what their manufacturing challenges are. So those have been, for the first 4 years or 3 years, that's the only way I met any customers. It just took lots of effort, cold emails, cold phone calls, lots of no's, lots of non-responses. In the last 2 years or so, we've tried to do a much better job of getting our website up to speed. So we put more educational content on there. We've done a better job marketing what we do and trying to put articles out in industry magazines, or do podcasts like this, honestly, help people understand what it is that the process even exists, and also how it works and how it could be used for them. So I am constantly amazed at people that come to us that have a part and an industry that I've never heard of. And sometimes it's a material I've never heard of. And I would never find that, just going and looking for it. And so that sort of inbound requests have grown a bunch in the last 2 years or so, and that's been critical to us. It makes it a lot easier on our side. We can sort of respond to some of these things, and also we learn about new industries and applications constantly that we didn't know anything about, and that's both exciting and valuable for our business.
Awesome. And how big is the team now?
So we've got 8 people now, and running out of space, and probably need some more people here soon. But the space we're in terms of hardware, capital equipment, it's time and money and intensive. And so I never expected that we would sort of in 4 years grow to $100 million and sell the business. That was never my plan, never thought it'd be realistic. And so we're on a slower path, but now have been around long enough to be involved in longer term projects with bigger customers and clients. Many times these components, a part for a jet engine, they might start working on the design and manufacturing of it 5 or 8 years before it ever flies. So you've got to sort of be around at least that long just to even be in the conversation with some of these applications.
That's awesome. And so what are you looking forward to kind of in the coming months and in the next year? What's on the radar? What's on the growth map?
Yeah. A couple things. We're building some more equipment that should have more capacity to work on. We've had some customers come to us with much larger parts that we couldn't fit physically. And so we are expanding the envelope so we can work on those. We've got some interesting government research grants that allow us to further our technology and really help solve problems at the fundamental level instead of just being reactionary to a need in what we have. In particular, we're working a lot on trying to de-risk and lower the upfront cost of this process. So often it can be kind of expensive to make the electrode, design the electrode, go test it in the process, figure out what sort of geometry you created, and then iterate off of that, dealing with how you flow electrolyte and what parameters you run. It can be quite iterative because the electrochemical process is so interactive. All the variables influence each other. So trial and error has sort of been the historical best way to do that. But we are working now on more sort of automation and simulation techniques to try and reduce those barriers, both to make it cheaper and easier for us to get to the first iteration, but also need fewer iterations because there's more intelligence built into the machine. So we've been starting to work more on that side of things, which not only helps you in the development, but in production too. Now you've got better tools to keep track of how the process is evolving and that it's in the right window when you're making tens of thousands, hundreds of thousands, or millions of parts. Those are sort of critical pieces for us. So those are all exciting things, coupled with some interesting customer projects that I can't really discuss, but they're all coming down the pipeline.
Awesome. Cool. Well, if people want to find out more information or they have a part or want to see more about the process, where would you point them?
Yeah, to our website would be the best place to go. And that is voxelinnovations.com. V as in Victor, OXEL, innovations with an S. And there's a section on there called education. It's really just a bunch of blog posts where we try and explain about how you can apply our process to certain areas, where it works and where it doesn't, comparisons to other manufacturing processes. If you know CNC machining, it'll compare how this is similar and different to that and where it's got strengths and weaknesses, or EDM or photochemical etching. So I would encourage you to check that out. I often tell people, if you are working on design of a component and you don't know all the manufacturing processes that are out there, it'd be easy to miss improved design, something that's got a thinner wall or more contour to it or something that you didn't know was possible, or there's a way to make that realistically. So even just a broader understanding of all the manufacturing processes available to you can help you design better parts and give you more options when you get to the manufacturing phase.
Awesome. Cool. Well, I appreciate the time. Hopefully everyone goes and checks it out, and hope to see you in person at one of these trade shows, or maybe if I have a part, I'll send it your way.
Yeah, great. Thank you, Mike.
All right. Take care.
Thanks.